Hi, everyone. Now that you all have a good understanding of the three states of matter, we are going to move on and investigate what exactly happens during phase changes. This image is showing us some dry ice. We are going to be working with H2O in our lab that's coming up. And in the simulation lab we're going to look at today, they also use H2O. So our learning goals today is to explain why the temperature of the substance does not change during a phase change, even though heat is continuously added or removed. We're going to look at and analyze a heating curve and cooling curve. Sometimes scientists call them an endothermic and exothermic curve. Those are vocabulary words that are actually coming up in our next unit. But for our purposes in the States of Matter unit, we say heating curve and cooling curve. And I'll talk more about that in the next couple slides. We're going to describe the relationship between melting, freezing, condensation, and evaporation. Recognize that phase change requires energy to be added or removed from the system. I think we've already talked about that quite a bit. And then identify the direct relationship between energy and molecular motion or vibration. Again, we've talked a lot about that. Even when we were building our states of matter models, we know that we start in a solid phase where those molecules are just vibrating. And then as we add energy, specifically thermal energy, we see those molecules start to move faster, increasing that molecular motion. But first, I want you to make a prediction. Does the temperature of water rise as it's boiling? And explain your thought. Remember, there's no right or wrong answer here. This is just your prediction. You're going to click the link that will open up a simulation. If it asks you to log in, you're just going to log in with your Google account, just your school Google account that will take you to the simulation. And it looks like this. So I'm going to just click play so you can see our example of a heating curve. And I'm calling this a heating curve because it starts in a solid phase and heat is being added. So starting state is solid. And I'm just going to change the final state to be gas. And then I will click play in a minute. This is a little different than Gizmo or the other PhET simulations we've done where you can reset in the middle of it. I don't see a reset button, so I'm just going to wait to press play. So after you write your prediction, you'll move to slide 3. And like I said, scientists refer to these curves as an endothermic curve or an endothermic graph. We're going to be referring to this as a heating curve. So explain why this is an endothermic graph from left to right. Why is this a heating curve? Well, take a look at the temperature. What is happening? It's going from negative 100 degrees Celsius to 200 degrees Celsius. So what's happening? Why are we calling it that heating curve? And then what is the liquefying point? We've been referring to it in class as a melting point. When does that solid become a liquid? What is the vaporizing point? When does this solid turn into a gas? Or when does this solid turn into a liquid and then to a gas, the vaporizing point? So if I were to click play, you can see that temperature is added. It's telling you what phase it's in. And now we see that some melting is happening. It labels what's going on in this heating curve. I'm just going to give it a second before I pause it. And there you can see it turned into a liquid. So just take note of the temperature and what exactly happened here when it was changing phases. So you'll answer these questions after observing that simulation. So more questions about the heating curve. It's asking you to place a star on the line segment that shows an increase in kinetic energy. Remember, we talked about kinetic energy as being the energy of motion. And I was kind of playing around with this earlier, but I'm going to just remove these. Oops, there we go. Energy of motion. So when do we see a temperature increase? When is that graph moving? I see it here and I see it 2 other places. Energy is being added and temperature is increasing. That's energy of motion. There are spots on this graph or points on this graph, I should say, where there is potential energy being stored. So that is not the energy of motion. It is the potential that energy will begin to move, but it's not moving yet. And that's indicated by these flat lines here. And it's asking you in question 5 to place a smiley face where you see an increase in the potential energy or that stored energy. And then question 6 asks, how much heat did it take for the sample to melt? Did the temperature change? So remember, we started in a solid. How much heat did it take? If you're looking down here at the kilojoules, or that's 1 unit of energy, how much heat did it take for the for the sample to melt? If you're not sure, go back at that simulation and click play. It labels at each point what's happening during the phase change. And then for question 7, how much heat did it take for the sample to boil? Did the temperature change? So again, you know that it was a solid here. We just observed that at this point 0, it was melting. It became a liquid. Well, now we know that after liquid, if we keep adding heat, the phase change happens and it turns into gas. So you're just taking a look at exactly exactly how much energy or heat it took for the sample to boil down here. Okay, so the next couple slides are an exothermic graph or a cooling graph. That's when the substance is starting in the gas phase, and then we are taking thermal energy away. So you can see that we started with H2O at 200 degrees Celsius, and we're ending in a solid. So this is a cooling curve. By the end of this cooling curve, H2O will go from a gas to a liquid and then end in the solid state. So it's just the opposite of the heating curve. The first question is explaining why this is an exothermic graph. It goes from left to right. Why is this a cooling curve? What is the solidifying point, or when did it freeze? When did it become a solid? And what is the condensing point? So you are answering the same questions as you did on slides 3 and 4, but this time you are looking at a cooling curve. And then these last real world connection articles, I'm not sure why they call them articles, because they're just little almost captions to me, and it's asking you to summarize what you read. And summarizing in science is a great strategy because it helps readers make meaning of complex science concepts. This isn't obviously a lengthy article that you would need to make meaning and summarize, but it is a helpful strategy. So this is asking, why does ice float? Most solids have a greater density than liquids and gases. However, water is one of just a few substances that has a lower density in its typical solid form than its liquid form. This is why ice cubes float on water. So if I were to put that into a summary, I could say that ice in the solid state is more dense than, actually I should say H2O. H2O in the solid state is more dense than H2O in the liquid state. So just a simple summarizing sentence for each of these real world connections. The next one is talking about plasma in your TV, what state of matter is involved in a solar storm, and then the last one, what state of matter is lightning. So if you guys have any questions while you're working on this, please reach out via email, and we will go over this tomorrow.